Hi, this lesson is about how to solve a system of linear equations using determinants. So, what is a determinant? A determinant is a quantity that is organized into a matrix. So, it's basically what is the value of the matrix. So, if I have a matrix, a 2 by 2, A with row A, B, and C, D, then the value of the determinant or the determinant of A is AD minus BC. So you multiply A times D and then minus the product of B times C. So a matrix of the form A, B, C, D is called a square matrix because it is a 2 by 2, 2 rows, 2 columns. And so these next few examples will allow us to calculate the determinant of these matrices. So here's your first example. We want to find the determinant of this matrix. So we just do 3 times 2 minus 5 times -1. That becomes 6 plus 5, so the determinant value is 11. Now we go to part B, immediately to the right. So we multiply -4 times 5 minus -2 times 1. That becomes -20 plus 2. So the determinant value here is 18. -18. So any real number could be the value of a determinant. In this next example, we're going to solve this determinant using what we know about how to evaluate we're going to use this matrix using what we know about how to evaluate a determinant to solve for x. We have an element here with the variable x. So I want to do 2x times -1, that's -2x minus 3 times 1 equals 5. So I get -2x minus 3 equals 5. Add 3 to both sides, and you get -2x equals 8. And so therefore, x is equal to -4. Okay, so we have a rule called Cramer's rule, which uses determinants to solve a system of linear equations. And we're going to be able to use Cramer's rule in both a 2 by 2 system with 2 variables, 2 equations, and then later in the lesson we'll use Cramer's rule to solve 3 equations with 3 variables. So the rule says that I can evaluate x by taking the determinant of the leading coefficients in the denominator, and in the numerator it'll be the leading coefficients of y, but the constants are going to replace the x column. So it's almost the same as the one below, except the variable that you're solving for, which is x, that's associated with column 1, that gets replaced with the constants. And then you evaluate the determinant of the numerator and the denominator, and then that ratio gives you the value of x. To solve for y, the denominator will be the same. It is the coefficients of the x's and y's, but this time because you're solving for y, it's the second column in the numerator that gets replaced with the constants. And then you evaluate each determinant, and the ratio of that is the value of your y. So remember, a solution, when you find a solution, that's an independent system, and if you do have an independent system, you should have an x-coordinate and a y-coordinate. So we're going to apply Cramer's rule to solve this system. 3x plus 7y equals 22, and 4x minus 3y equals 17. So the coefficients of x and y are the denominator, and the numerator, I replace the same matrix that's in the denominator, but the first column gets replaces the numbers that you see below. So now I evaluate this determinant. On the top, it'll be 22 times -3 minus 17 times 7. So I get -66 minus 119. And then in the denominator, it'll be -9 minus 28. So this becomes negative 185 divided by negative 37. So my x value is 5. So if you find a solution for x, you will certainly be able to find a solution for y. So the denominator will be the same. So my denominator here is going to still be negative 37, but this time the second column is what gets replaced with the constants. So the first column should be the same as below, 3, 4. So I have to evaluate that determinant on top. So it's 3 times 17 is 51, minus 4 times 22, that's 88. This gives me negative 37 in the numerator and negative 37 in the denominator, so the y value is 1. So your solution is the 0.51. So this is yet another option to solve a system of linear equations. So in earlier lessons in chapter 10, we talked about how to solve a system using substitution method, the addition method. Then we did Gaussian elimination and Gauss-Jordan elimination, and now we have the option of Cramer's rule. Any of those choices would give you the same result, a solution of 5, 1 for this problem. Okay, here's another one. I have y is equal to 2x plus 3. That's our first equation, and negative 4x plus 2y is our second equation. In order to set up your matrix, in order to evaluate the determinant, your first equation has to be set up the same as the second one. Your x's and y's have to be on the same side and your constant on the other. So that's the first thing I did. I rewrote that first equation as negative 2x plus y equals 3. And now I can pick up my matrices. The denominator will be negative 2, 1 in the first row, negative 4, 2 in the second row. And in my numerator, the constants replace the first column. Otherwise, the second column should look the same as below. When you do your evaluation, you get 6 minus 8 on top. You get negative 4 minus negative 4. So I end up with negative 2 over 0. When you get something like that, where your denominator is 0 and your numerator is a different number, that's going to be an inconsistent system, which means there is no solution. So you don't need to continue and try to solve for y, because you will get the same result. You'll be dividing by 0. So that means these two lines would never intersect because they are parallel to each other. So here's another one that we're going to solve by Cramer's rule. So I have 6x plus 9y equals negative 3, and negative 2x minus 3y equals positive 1. So this is already in the right format. So I just pick up the coefficients of x and y that goes into the denominator, and the first column gets replaced with those constants. Otherwise, the second column should look the same as the denominator. So when I cross multiply, I end up with 9 minus 9, and I get negative 18 minus negative 18. This is a different result than what I got up here. When you get a 0 and a 0 in the numerator and the denominator, that is the case of a dependent system, which means there are an infinite number of solutions. So if you solved for y, you would still end up with the same result. So I didn't really show that work, but you can use Cramer's rule to figure out what y is, and you'll end up with the same scenario. So the challenge with a dependent system is, how do you present the solution? So I need to solve one of these equations for y. It doesn't matter which one you pick. I picked equation 2 just because the numbers are smaller. If I pick equation 1, it's going to work out the same way. So when I solve equation 2 for y, I added 2x, and then I divide everything by negative 3. So my y is negative 2/3 x minus 1/3. So if I let x equal a, and I plug in the a right in here, my solution, or my solutions, are the points a, negative 2/3 a minus 1/3. which means A can be anything. You can pick any number you want for A, and you'll be able to figure out the Y by plugging it in here. And so if I let A equal 0, then my Y will be negative a third. This is one solution on this system, but there are infinitely many of them. So this is the general way to express that. If you're not told what letter to substitute in for your variable, then you could present your solution as just x negative 2/3 x minus a third. Okay, if they tell you to let x equal, let's say, t, then your answer would be t negative 2/3 t minus a third. So reading the directions carefully is important, so you present your solution as expected. Okay, so there is a 2x2 system for you to try. You can apply Cramer's rule here. So the first equation is x plus y equals negative 5, and the second equation is 3x plus 2y equals negative 13. Could also solve it with a different method and see if you get the same solution. So the more options you know, the more tools you have to solve a system. All right, so that's for you to try. Now we're going to talk about how to evaluate a determinant of a 3x3 matrix. And a 3x3 matrix, you're going to have two options here. And so the first option is a bit of a shortcut. And so the shortcut is that you copy your matrix down and then rewrite column 1 and 2 immediately to the right of that matrix. So only the first two columns get copied immediately to the right. And then you have to multiply. And you have to multiply in a very specific order. You have to multiply on a diagonal from left to right. And so 2, negative 2, and 3 is this product here. And then plus the next diagonal. So negative 1, 4, and negative 1 is here. And then the next diagonal, which would be plus 0, negative 3, and 1. So those products would all get added together. But in order to get the value of the determinant, you also have to go on a diagonal in the other direction. And so when you go in the other direction, you're going to subtract. So this is minus 0 times negative 2 times negative 1, minus 2 times 4 times 1, and minus negative 1, negative 3, and 3. So you should have a diagonal of 3. So in other words, you wouldn't be choosing this because there's only two numbers on that diagonal. So those products work out to be negative 12 plus 4 plus 0 minus 8 minus 9. And when you add and subtract those numbers together, you end up with negative 25 as the determinant value. Okay, so here we're going to apply the same technique. We want to find the determinant of this matrix. And so remember, the trick is to rewrite the first two columns immediately to the right, and then you're going to multiply on a diagonal. So I just wrote the results immediately below. So the first diagonal is 0. The second diagonal gives me a result of negative 5. The third diagonal gives me a result of negative 18. So those all get added together. Okay, now I go in the other direction, and you want to start from right to left and getting a diagonal of 3 numbers. And this is when you're going to start subtracting. So negative 3, negative 2, and 30 gives a result of minus 30. Then 0, 1, 3. 0, 1, and 3 is a result of minus 0. Negative 1, 2, and 4 gives me a result of minus negative 8. So again, adding and subtracting those results together, give me a result of negative 45. So that is the value of your determinant. Okay, so we have to know how to evaluate a determinant in order to be able to use Cramer's rule to solve a 3 by 3 system, but there is more than one way to solve a determinant or to find the value with a 3 by 3. And so you really only have to master one method. Again, knowing more than one way is good to know in case you forget one or you find one easier than the other. So with this method, we're going to be using these signs to help us organize our matrix. And so it's just an array of signs, plus, minus, plus, minus. They're alternating all throughout, but you start with a plus, and then they alternate from left to right, and up and down. You won't have any two signs that are the same next to each other. And that'll be important in a minute when I explain what you're doing. So here's my matrix. So the way this works is that you need to pick one row or column, and that's going to be the row or column that allows you to then create these minor matrices. And minor matrices will be 2 by 2 matrices. If you have a 0 in your matrix, you definitely want to pick either the row or column associated with that 0. Since I have a 0 here, it would be just as convenient for me to use column 1 like I am, or row 1. It would give you the same result. But anything with a 0 makes your computations easier. So if you don't have a 0, it still can be done, but it's just a little bit more to compute. So the 0 is in a positive position. Okay, so that means this is going to be plus whatever I write immediately to the right. So it's going to be 0 times the minor matrix that's left when you cross out the row and column associated with the 0. And that minor matrix are these 4 numbers, and that goes right in here. Negative 2, 1, 3, 4. Okay, but remember I picked the first column as the column that's then going to drive the rest of this, and the 2 is in a negative position. So that's why I have to subtract at this point. So it's minus 2 times, and I'm going to eliminate the row and column associated with the 2. And the numbers that didn't get crossed out are what go in here as my minor matrix, negative 1, negative 3, and 3, 4. And then I go to the third number in that row, in that column, which is the 5. The 5 is in a positive position, so that's why I write plus 5 here. And then cross out the row and column associated with the 5, and these 4 numbers that are left are my minor matrix, negative 1, negative 3, negative 2, 1. Okay, so now I have 3 matrices with a coefficient or a scalar in front of each one. So we know how to evaluate the determinant of a 2 by 2. It's basically just these 2 numbers minus these 2 numbers being multiplied. And so that'll be 0 times negative 8 minus 3. That's why I said the 0 is really convenient, because this whole thing is just going to work out to be 0. And when I go to the next one, this works out to be negative 4 minus negative 9. So this whole thing works out to be minus 2 times 5. And I go to the third one, that's negative 1 minus 6. So this works out to be 5 times negative 7. So the rest of it is just a little bit of arithmetic. Combine those products and then add and subtract your numbers. So you get 0 minus 10 minus 35. Here the sign is the same, so you add them, and so the matrix value is negative 45. So I did this same 3 by 3 matrix earlier using the other method, and we got the same answer. Okay. The 2 by 2 matrices evaluated after eliminating one row and one column is called the minor matrix. So that's what we mean by the minor matrix. Okay. All right. So now we're going to solve a system of linear equations using Cramer's rule, where we have three variables and three equations, which means we will have a 3 by 3 matrix. So we'll use either one of the techniques that I just explained. So first, let me give you the formula. But again, the formula looks kind of a lot to memorize. But if you can remember the pattern, it makes it a lot easier. The denominator for x, y, and z will all be the same. All of these denominators are just the coefficients of x, y, and z. So the first column are the coefficients of the x's, second column are the coefficients of the y's, third column are the coefficients of the z's. So once you figure out one of them, if I'm solving for x, it will be the same number for the y and the z. Now, in the numerator, whatever variable you're solving for, you're going to replace that column with the constants. So here, if I'm solving for x, instead of having a's in column 1, I'm going to have my constants, which I'm calling d's, in column 1. And column 2 and 3 will be the same as what's below. When I'm solving for the y's, column 1 and 3 will be the same, but the second column, the y column, gets replaced by the constants, which I'm calling d's. And when I'm solving for z, the first two columns stay the same, but this time, see, these two columns stay the same in the first two columns, but the last column, the z column, gets replaced with the d's. Okay, so hopefully those formulas make sense. So here we're going to solve this with Cramer's rule, and I solved this same problem in an earlier lesson using another method, and I'm going to get the same result. So first, I'm going to figure out what my denominator is. It takes a lot of space to write it like that. So I'm just going to get the denominator, because whatever I get there, it'll be the same number in the x's, and to solve for the y's, and to solve for the z value. So I need to find one x, one y, one z, unless it has no solution or infinitely many solutions. So when I put all of my coefficients in here, this one doesn't have an x, so I have to put a 0x here. So I get 1, -1, -1, 0, 4, and 1, -1, 1, and 3. So I use the first method where I copy the first two columns, and then I just multiply on a diagonal and add and then subtract those results. So the first diagonal is -12 plus 1 plus 0 minus, and that works out to be 4 minus 1 minus 0. And adding and subtracting those numbers give me a result of -16. -16 is not an answer, but it will be used to help us figure out what my solutions are to x, y, and z. All right, so now I have to figure out what x is. So x, you're going to take the same matrix that I had up here, except the first column will get replaced with the constants. So I should have 2, 7, 2 in the first column. And then I did the same technique. I repeated the first two columns and wrote them here on the right. And then I multiplied on a diagonal. So 2, 4, -3 gives me -24. Then plus -2. Then plus -7. When you go in the other direction, you have to subtract. So it's minus -8. Then minus 2. And then minus 21. That all works out to be -48. But my x is the ratio of those two numbers that I just found. It's the determinant of the x coordinate, the numerator, divided by the determinant of of just the coefficients, which will be used in the future calculations. So negative 48 divided by negative 16 gives me an answer of 3. So remember, we need to find an x, y, and a z. So my denominator I know is negative 16. I don't need to do this again, but I'm going to take that matrix, but this time the second column gets replaced by the constants. So there's that 272 in the middle. Again, repeat the first two columns and multiply these numbers on a diagonal. This will be negative 21 plus negative 2 plus 0. And then when you go in the other direction, that's when you subtract. So I get minus 7 minus 2 minus 0. That works out to be negative 32. So that means that my y value is negative 32 divided by negative 16, which gives me a value of 2. So far we know x and y. Last thing is to find z. So again, you take the denominator that you found at the beginning, but replace the last column with the constants. The rest of the numbers should stay exactly the same. Repeat the first two columns immediately to the right, and then multiply these numbers again the way I explained, and this time you get 16. So my z value is 16 divided by negative 16, which is negative 1. So the solution, x, y, z, is 3, 2, negative 1. And you can always plug in those numbers back into any of the original equations, and it should make the left side equal to the right side if you did this correctly. And this one does work. Okay, here's another one. I have this system of equations. And so again, the first thing I did was look for what the denominator will be, which are all of the coefficients of the x's in the first column, y's in the second column, z's in the third column. Again, I repeated the first two columns immediately to the right, and then I multiplied. So I get negative 8 plus negative 6 plus negative 3. And then when you go in the other direction, you have to subtract those results. So that works out to be minus negative 4. So this is minus negative 4 minus negative 9, and then minus negative 4 again. So there are several numbers to add and subtract here, and they all cancel out. So that means that my denominator is going to be 0. That's a problem. So I need to figure out, does this mean that this is a system with no solution, or is this a system with infinitely many solutions? If I get 0 in the denominator and a different number on top, let's say like negative 5, then this would have no solution. But if I get a 0 in the numerator and the denominator, this would mean it has infinitely many solutions. So I know that it's not an independent system because I got a 0 in the denominator, but I don't know which of these two scenarios it is until I compute the numerator part. So I'm going to compute d sub x, which means that these constants replace the first column in that determinant. And so when I do my computation here, I get 0, which means I have this scenario. So that means it's a dependent system with infinitely many solutions. And so here the directions say, let z equal t, then represent x and y in terms of t. So we do need to do a little bit of algebra to then present our answer. I know that I'm going to let z equal t. So what I did was I took two of the equations, and I just need to look back. Oh, it's equations 1 and 2, and I subtracted them because what I want to do is I want to solve for y. So when I subtract equation 1 and 2, the x's will cancel, and I'm going to be left with negative y plus 2z equals 3. Subtract 2z over to the right, and then divide everything by -1, you get that y is equal to 2z minus 3. But z is equal to t, so that means that y is equal to 2t minus 3. Well, now I know what z and y is in terms of t, but I need to figure out what x is in terms of t. So I'm going to substitute this and this into equation 1. You could choose equation 1, 2, or 3. I chose equation 1. It's a simpler one, and I'm going to solve it for x. So I have x plus 2t minus 3 minus t equals 0. These are like terms, so you get x plus t minus 3 equals 0. Then subtract t and add 3, you get that x is equal to negative t plus 3. So your solutions, because there's infinitely many of them, is negative t plus 3 for x, 2t minus 3 for y, and t for z. Okay, so here's one for you to try using Cramer's rule. Notice that in this system, I don't have a y term here, so you should put a 0 to hold its place in the matrix. And I don't have a z term here, so you should put a 0 in its place so that your matrix stays organized. But you should have a 3 by 3 matrix, and then compute your x, your y, and your z, so you will be evaluating several determinants of a 3 by 3. So that's it for that lesson. Good luck.